Lelio Di Martino, who is joining us from Brazil. Now, Lelio Di Martino has been a research scientist at the Nokia Bell Labs since 2015. He has contributed to projects including resiliency testing of telecom operator networks, data processing platform for health analytics and anomaly detection of transport optical networks, and SLA-driven networking for enterprise-grade private wireless networks. Also, Internet of Things, programmable networks and virtualization projects. He was also the architect for the first release of the ENSA's NetUnix programmable network OS, and he made a significant contribution to supercomputing dependability and resilient high-speed networks. Now, Lelio likes to invent things or devices, if you like, to automate his home. Most of the time, they don't work as expected, making his main client, which is his wife, extremely unhappy. But not to worry, this will all make sense in a moment, as Lelio's presentation today will be about chaos engineering. So, chaos engineering as a service for cloud-native telco. Lelio, the digital space is yours.
Thank you very much for the super introduction. And indeed, part of this talk is inspired by the chaos that I created in my home with all my inventions that don't work. All right, just kidding. So I wish I was there physically to say, are you ready to unleash some chaos here? Because this is exactly what we're going to do today, to understand how we unleash chaos in a controlled way for making our networks, making our communication more resilient. And why is that? Because we do live in a connected future. Actually, the connected is right now the present, and the future will be even more. The truth is, networks were never as important as today. So when the pandemic hit, we became more and more dependent on the network to reach out and communicate, but also to guarantee safety in business critical teleoperations and keep producing critical goods for society. Now, let's do this exercise. Imagine a future where networks are everywhere with infinite capacity and latency that will last less than the time of a spark. These networks in the future will be doing things wirelessly that only you can dream of today. But more importantly, these networks will not be just there. They will be brought to you, brought where it's needed by an AI. The capacity will be adjusted. The SLA will be created on the fly, and robots and the interfaces will be connected in ways that we never thought possible before, and more importantly, that we never tested before. This is why we are creating network digital twin to understand what-if scenarios where data will actually be flowing to understand, okay, what happened if I change this thing? What happened if I change another thing? The problem is, however, that there will not be one single network to do it all. The problem is that there are so many SLAs that can be composed dynamically in this vision by an AI that makes really impossible to have one network deployed there like we have today. It's not only that, it depends also on the time of the day. In the morning, you're probably downloading your email, or you're storing things on your Dropbox or your OneDrive and so on. In the night, you're watching Netflix. And in some countries, that accounts for up 70% of the utilized bandwidth. So can you imagine now how we can optimize a network if things are changing continuously? The real challenge here is really how to go beyond best effort connectivity that we have today. And indeed, in this space, telco is really changing perspective. We are going from the hard phone that you can see here in this picture, invented by Bell Labs, by the way, to something more volatile, more ubiquitous, where network will be brought where it's needed, physically or virtually. And this is why telco is embracing the cloud-native philosophy, where things will be deployed as microservices, potentially in highly reliable, highly available clouds, so that it makes possible to virtualize, disaggregate, connect, use open interface to create next generation of communication systems, like Amazon and Netflix are doing for their specific services. Let me ask you a virtual question here. What will happen if the network fails there? That's a very tough question because all these microservices, they can be composed in any possible way at one time, depending on the SLA that you have. Now, the real question that we are trying to address is how can we even test against something, an SLA, for instance, that the network should provide you that will only be decided at runtime? And how are we doing well in this space? Well, probably Amazon, Netflix are doing with their systems, and I will touch on those things later on. But for the network part, not that much. We still are in a space where we have it's such a big testing space that we cannot even dream of exploring it and testing a network exhaustively. In fact, 33 to 64% of telco outages are due to untested configuration and corner cases, things that happen once in a blue moon. But when they do, they will disrupt the entire networks for several hours, causing several millions of damages, if not critical threats to humans. And this is why we are here is because we are coming from this past vision on reliability. This is a citation of Jim Bray, one of the pioneers in system reliability in the 80s and the 90s. And basically, in the 90s, a way to improve availability is to install proven hardware that you test under the rain, you test under the sun, with snow, with the sand and everything. And you put your software that you test and validate exhaustively, and you leave it alone. You don't touch for years. We are not anymore into this space because we are touching our network at least once a week or more to optimize, to upgrade, to provide more services, to be always one step ahead of the market demands. But in all this, there is only one big truth, that failures are a given. We cannot do much. We have to embrace them. We are not in a situation in which we can test things before we deploy in an extensive way. We need something more. And let me give you just an example here. So this is some data that we collected over the year. And on the left-hand side, you can see the hardware failure rate curve for some hardware for telco. And the right-hand side, you can see the software failure rate for some system software and communication software. Now, there is one beauty about hardware, is that after mortality, infant mortality part, where the hardware is defective, boards are not working as expected, so you replace the board, then you go in a constant failure rate here. So in this case here, in the yellow part, this is the field, the first office applications or pre-testing, pre-deployment things. So you find the problems, you fix them, and then you move to the production where you have a nicely constant and predictable failure rate. Let's look to the software here. That's the idealized curve. If the software was like the hardware, we'll have like this. But instead, the failure rate increases over time. Why is that? Because every time we have major software upgrades and we discover new bugs, we discover new things, and then we release new patches that will bring down the curve, but then it goes up again with the new software upgrades, and then it goes down again with a patch. So this tooth-so curve here, it's really something that we need to deal with. And we need to understand how we can tolerate those failures. So the actual curve is something way different from the idealized curve. The real question here is how much confidence can we have in the system that we put in production? And the answer is we should have the highest confidence possible. So indeed, software quality is among one of the major market pain points for the 5G, for connectivity, for optical networks, and so on. So there are software quality and bugs in software that are really creating some disruptions or preoccupation, I will say, in the market, but also the long-time delivery solution, because in order to reduce the power of the bugs, we need to test more. This will impact on the lead time. And that basically means that our products will be old before we even reach the market. The truth here is that as we are today, the cost of testing and troubleshooting, for instance, new features in a 5G network, it's anything between 40 to 70% of the total delivery cost of that specific feature, which is very high. Let me give you an example here. So in 5G radius, for instance, imagine that you have an example and you have several engineers involved for doing the upgrades. So basically here, what you do is that you have, say, 48 engineers here. These numbers are normalized, by the way. 30% of the engineers are for the upgrades, and 70% of those engineers are actually performing troubleshooting on 5.8% of the failed nodes. So you do have failures in the upgrades. A small part of them, 5.8% of nodes are failing, yet they require 70% of the workforce there. And the reason is that because 80% of the things that are happening when you're performing a new software upgrades, yes, you already observed those in the past, but 20% are new and unique, and they require a long time to debug. And the reason because of that is that if this is a cloud of microservices here and this service fails, it generates some entries in the data, in the logs, into everything that you have. This activation here, basically when this happens, you have an error. If that error gets activated actually and propagates, it became a failure. Otherwise, gets just a latent error. So the event log actually, they have lots and lots of things inside, and the event logs are the tool that we use for debugging these systems. Now, only a small part of those failures are actually reported into the event logs and are called reported errors, while all the others are reported, untraced, are even errors that we are not even aware of. And this is exactly the data that we use for training people as well as machines in understanding how to detect when things are going wrong. And you can understand that this data is very noisy, and there are lots and lots of error failures that can happen, but they are really it's like finding a needle in a haystack. It's a very difficult problem to solve. Yet we use this data to, after years and years of deployment, to understand what's the best practice of changing your system. But your system changes continuously because we are always upgrading the system every time. So this is really not a viable approach right now. And in addition to that, there is really a limited observability. So how do we enable continuous testing and improvement into this network? That's actually the key focus of this talk. And basically, from our experience, we saw that 18% of outages are configuration issues. So things that are actually somehow due to some human intervention on the network, on the system, on the software, on the testing, and so on. 54% of these outages are procedural because the system is so complex that probably the procedures that will work in the formal release will not work as expected into this release. And then more than that, 20% of the alarms are not even detected when you do lab applications. And because our networks are very big, there are several hundreds of thousands of sites. And of course, in lab testing, you have probably one or two that you're using. So the sample size is very small. So the space of all the states, it's not really sampled in the best possible way. So how do we do testing today? So basically, we have one part of the activities, as I said, lab activities or first office application. Then we have the deploy activities, and then we have the part that goes, the network is in production, right? So in doing this, we perform regression. For each new software release, we perform regression testing, of course, to understand whether the feature that we have is actually working as expected, and we have or breaking something else. Acceptance testing to see test whether the feature is actually doing what it's supposed to do in the way that it's supposed to do. And finally, soak testing. Basically, we let the software soak inside the network for an extensive period of several days to weeks to understand whether we have a long run on degradation on some KPIs in the long run. What we propose here is to augment this with chaos testing. Chaos testing that allow us to reduce the testing time and do something more. Basically, by deliberately crashing the system, and I will tell you how we do that, we generate very valuable data that from one end can go and create what we call a test and outage data lake that will allow us to train people and machines in a better way. On the other end, this will go to reinforcement learning algorithms, machine learning algorithms that allow you to basically detect things when they go wrong, even before they go wrong, by using the generated data, by spontaneous data of the system, like logs. Finally, we want to use that also to understand how well we are testing and provide feedback to the testing part, because choosing the right test case, it's one big problem for testing a specific feature. And sometimes when you have the integration and you integrate a very complex piece of software together, most of the time for testing is exactly for creating effective or not effective test cases. So let me focus on these 20% of alarms that are not detected into the lab testing. That basically means if these are all the possible states that are tested into R&D lab, in the first office application, in customer lab, and so on, we still have 20% of states that are not even traversed, not even exercised, not even tested there. And that's something that is worrying us. The chaos testing will use part of the production network, if not all, to test in production in a safe way, so that basically we can identify untested states, because we all know production systems are unique. We cannot even dream about replicating them into synthetic lab environment. We'll never reach 100% confidence. And the idea is that if this is the curve from the defects that we inject in each phase of the system development or software development, like in the coding and so on, and on orange is defect founds, the more we go forward to fix the things, the more will be expensive, right? So with chaos testing, what we want to do is to do testing left shift, to take that curve and shift it to the left, so that we can inject real failures, like failures that are mimicking real world situations inside our lab, and decrease that 20% of alarm not detected in a ways that we can optimize our testing. The chaos-generated knowledge actually enables the cost reduction in troubleshooting and outage, and also for managing the outages costs, like how do we recover from field outages. So let me tell you now how this works. The idea is pretty simple, and is exactly what is happening today with us. It's really about injecting something harmful in a controlled way, study the reaction and build immunity. This is exactly what it is. To inject something to crash the system in a controlled way, so that we can observe how the system crashes, and if, first of all, if it crashes or tolerates the faults, and how it crashes, what's the impact of the fault, and so on. And this is done by choosing carefully chaos experiments. So I like to call it experiments, because to me, those are scientifically planned experiments, not tests. Because you have a problem that you are studying is how your system reacts to that failure. And you have a way of doing that is by killing your system. Now, depending on what you inject in your system, like faults that will simulate hardware failures or software shutdowns or network misconfiguration and so on, you are able to get hints on how the system will react to these situations. Right. But you tell me probably, well, you know, Netflix has been doing that since 2016, and Amazon does that in game days and so on. Well, I can tell you that our systems are a little bit different, and networks do require a different type of chaos. On the right-hand side, you can see here that a typical node B, a typical node of our 5G network, for instance, has more than 70,000 KPIs. And with 5,000 more different counters and 9,000 different alarms. The idea is that if you put all these things together, jointly with all the possible configuration that you have basically infinite possibility. Okay. On the web scale, instead, on the left-hand side, you have also a one-to-many relationship in which you do one testing, the testing will impact on the service, and then basically that service is impacting on millions of targets, platform, and consumer. Like, let me kill a basic service of Amazon EC2, and let me see actually how that impacts on specific production workload, okay? Most of those services, sometimes they are stateless, things that will never happen in our network. It's very difficult that you find services in our network that are stateless, because you have connections. It's really managing the network in a way that you need to trace this connection between two endpoints, for instance. So in telco, we have almost infinite combination of vendors, configurations, and customer requirements. As I said in the beginning, each network is different from the others. So it's not like you test once in EC2 and you probably impact Netflix, you impact Facebook, you impact WhatsApp, and so on. Here you need to test one for one specific part of the network, or one specific customer. And whatever you did today for that customer, first of all, will not be valid tomorrow, but for sure is not valid for another customer. So this is why it's really difficult. And this is the main idea, to prepare the worst by continuously embracing failures. Okay, so what I like to say is that enable what-if scenarios so we can unleash fault injection and chaos on demand. And the idea that we do that, we created a platform that embraces some of the principles of the chaos engineering. And basically the idea is that we have, in our telco clouds, networks are running in as a virtualized environment, in a virtualized environment. What we do today, we have ways in which we can inject faults in production by cloning specific pieces of the network and running those networks into a network digital twin container, so that we can create what-if scenarios like kill something and see what happens without impacting the production network. That's basically the main idea of the frameworks that we have. And this is the closest thing that you can do for using the production system, actually to have a copy of the production system with that specific configuration. But let me go over the principles here. First of all, networks, they do have data plane and control plane. Here, we are claiming that we need to test the control plane, because the control plane is the most sensitive part, whether, if you kill something in control plane, then the data plane probably will be just hanging around without any control. So really what we focus here is providing control plane performance testing and also chaos testing. And the idea is really to run that in production to create what we call a testing plane on demand, and that we will be able to identify scalability limits and configurations, and at the same time to provide care to kill things around without causing any disruption to the production network. The second principle is that we need to use production workload, because the only way that you can force states in your system that are representative of the real world is only if you're working with real world workload and real world settings. This is exactly what we have. Try to understand what are the on-demand SLA and KPIs, understand the real network state, and try to use the most possible ways the traffic that is coming from the network as traffic for our test cases. And finally, we do test using the black box. This is the way that things are connected in runtime. They communicate using their interfaces, right? They don't communicate knowing the internals. So the interfaces are the most critical parts that we need to test. The interconnection between different components using the interfaces, and we do that. And we don't instrument, we observe things as happening as spontaneously possible by looking logs, looking system level KPIs, so that basically we understand whether that fault is actually well represented by the data that we collect and the system generates, like KPIs, or we need to do something more to improve the system observability. Now, in this animation, I will give you an example how we achieved a digital twin for the network for one specific use case. This is an SDN, software-defined network, transport network for a major operator. And basically, the idea is that everything is running in the telco cloud and is connected to several infrastructures as every virtual switches, okay? Especially the control plane is federated and attached to these infrastructure as a service virtual switches. Here, for instance, you might have the SDN controller that basically running a bunch of VMs or containers, and you have all the NFV applications and so whatsoever network functions on the other side that are using the SDN controller. The SDN controllers manages the topology, for instance, of the routers, and like they were SDN switches, for instance, and each SDN switch has different ports and elements attached to it. The idea is that the NFV applications asks the SDN controller to create service. The SDN controller takes all this information, understands what's the best possible path, for instance, and provision the path across the network. The request is from the NFV application to the SDN controller. It goes over the infrastructure as a virtual switch, and that's the production workload. When you do that, and then the workload arrives to the SDN controller, the SDN controller programs the path and provisions the routes and services and SLAs and whatsoever. This is the production data plane. This is the production SDN, or as we call this example, network under test. Now, imagine that we want to create chaos here. The idea is to have a campaign manager that will allow us to manage this testing as a service. And basically, the campaign managers receives a high-level definition of what is the test that you want to do, like inject fault inside the SDN control plane, inject the network latency, 100 milliseconds on latency for this much amount of time on this port between these two services with this period. Okay, so you can do that. You can describe that high level like a JSON. The campaign manager will take this information and creates all the testing resources that you need to run that test. So first of all, it creates a bunch of services like the data collectors, the topology manager, the experiment manager, and load generator that are basically, they do exactly what their name is for. So basically, the data collector collects the data for this experiment so that we start understanding whether the fault that I'm injecting actually is reflecting in the data or not. Topology manager manages the topology of the experiment, how many nodes I'm using in the experiment, if not the entire network, how many of those nodes should be connected, and so on. The experiment manager manages all the phases of the experiments, like creation of resources, configuration, and so on. And load generators finally does load generation or load interfaces with the real workload that is coming on the production network. So the idea is that when you receive this question, these requests, these elements will be attached to a network created on demand on the same federation on network virtual switches. And basically, we start cloning the production controller that is the target of our testing. When we do that, basically in cloning, either than physically cloning part of VMs or starting from some templates, we start and we create also another infrastructure as a service virtual switch that we call test plane. In test plane, what we do, we start using that test plane as a clone of the real control plane in the production network. So the experiment manager, in this case, what it does, it interrogates the SDN controllers and the virtual switches so that basically it gets all the status of all the possible communications, all the intents, network configuration, network devices that are managed, and basically clones those things to the topology manager into a virtualized topology that only shows the aspects, the feature of the network that are required for your testing. After that, the experiment manager basically starts replaying all the steps for creating the same status of the SDN controller, the production network, that now we have also into the testing plane. So this is the emulated data plane that we have here. Finally, we need to generate load for the cloned controller. So what we do, the load generator here, it interacts with the campaign manager, understands what is the configuration of the current workflow, and through port mirroring, decides to mirror 1%, 2%, 10%, 100% of the traffic to the so-created test plane. In doing that, basically, it can do also another thing. It can augment the traffic and use and over provision the traffic or overimpose to the traffic synthetic traces so that basically you can generate what if scenarios that are based on the real workload and actually more on top. To see, for instance, what will happen if I have 10 times more connection requests that I have today. So basically, this is the way that we achieve in production testing, but that's only one part of the problem. What we do after we test these things, we need to learn, and the learning is the hardest of the things, right? And the idea is that basically through our prototype, that actually now we are embedding in production networks, that is called FICO. We perform this continuous testing, and we have the injection data, which is what we are injecting right now, like network latency. I'm killing an OSGI component. I'm doing something else. So that's the injection data. And when I inject, that injection information goes to a data lake. Then we have data coming on the side that is the spontaneously created data, like workload logs. So when the injection happens, these two, they are giving me information on the ground truth. What is happening in the system, given that I know that the system is failing because of latency. So this information, they go to our data analytics algorithm that I will explain in a couple of slides that will allow us to extract knowledge and understand how we can create what we call a fault fingerprinting database that we can use for runtime for creating machine learning models for error detectors, or at the same time for just providing a feedback to the R&D departments so that they can create better test cases in the future. So there are several metrics that we observe. This is just an example of how we do things here. First of all, we have some network KPIs before the injection. Then basically, this is what happens during the injection. So you have normal operation, you inject the faults, then things start going south. Then you have the detection time, that is time that the system takes to understand that something is going wrong. Probably you have a reaction time, then the SDN recovery action takes place, for instance, in the SDN example, and then you have the recovery time, where the failure is removed. So the first one is called failure latency. So how much time do we take from the moment I inject to the moment that the failure actually creates some bad things in the network? And then we have the failover time. So when you do have this, what happens is that from a stable state before the injection, we go to unreliable states, and then we go to disrupted states. In those disrupted, these are the states that we are exploring in our testing with fault injection. And these are the states that usually you cannot explore with some other regular testing techniques. So jointly with the KPI before the injection, we monitor the KPI during the injection and the KPI after the injection. And we start building the hypothesis. You remember I say that these are carefully designed experiments. It's not just a test. So there is also a part of the hypothesis testing here. The hypothesis is the injected fault causes a substantial change in the steady state. We use this information to create a machine learning problem in which we use signal characterization to create like a picture of all the KPIs of the network and understand if that picture is very close to the picture that we saw before in other tests, to understand how that fault actually creates the similar effects of what we observed in other tests. And this is exactly how we do. So I'm not going to give you all the details about the equations here. So imagine that this is just an expression of the steady state of the system here. And it's a matrix that changes continuously each 1 second you have different steady states, and each metric here has different values. Okay, so this is the time window for a first sample, second sample, and so on. Then what we do, we perform a fast Fourier transform of this data. So we go from time domain to the frequency domain, so that basically we can extract the power spectrum of these KPIs. Into this power spectrum, we perform a moving windows of power spectrum values and analysis, so that we can understand on each frequency how much is the power of that specific frequency. That is it's an indication on how the KPIs are changing over time, for instance. Then, of course, we normalize the data so that we can normalize everything in between 0 and 1. Then we move the time window. We do exactly the same analysis, and basically we check whether the KPI time t is actually equal to the time of the KPI time t plus 1 in terms of frequency, in terms of powers, and so on. If that's the case, probably things didn't change. Otherwise, we estimate the medium square errors, and we populate a steady state variation index that will tell us for each of those KPIs how much those KPIs changed in frequency and in time after we inject the fault. So what do we do after that? We do exactly what is here. This is a picture that we generate for all these KPIs. And as a picture, we run that picture into invariant scattering convolutional network. It's a mouthful, but the idea is that basically we want to really have this as a picture and train something to detect how similar is this picture to all the other pictures that we had before. And it's exactly what happens when we call, for instance, one of our home, I cannot say the name here, otherwise my home here with all the devices will turn all the lights on. But basically when we call the Google Assistant or the Amazon Assistant, basically our voice is translated like in a picture that the DSP can process very quickly so that it can understand whether the comment that I'm giving is exactly what it's expecting. And this is exactly the same thing that we're doing here. The other thing that is way multidimensional with all the KPIs, and I'm using that to tell the system, can you tell me how close am I to these faults that you observed on similar system on this similar configuration? So for doing that, we have another algorithm, which is deep learning based on LSTM, on deep learning models, that will take all the traces coming from the field and very quickly will understand how those traces are close, similar to what we observed before. That was the learning phase. Here you go. So now in the remaining 10 minutes that we have, let me give you an example how we applied. So how the example that I gave you before for the SDN transport network actually produces some results here, and how we use those results to improve the product. So the idea here is that we had this SDN transport network. The topology was very complicated with many controllers all scattered in distributed regions and all federated in one single logical controller. Each of these controllers were handling different switches, and at the same time, all the information on the switches of this controller were propagated using distributed consensus algorithm to the other switches. Now the idea is that when you have requests coming into this switch here, basically this may require to program this switch here that this controller is responsible, but also all the others. So there is all this consensus going on. What we found here is that in these systems, when you have a failure, even a small 100 milliseconds network latency for a few seconds, these consensus algorithms start behaving very erratically. And they require so much time to reconvey and rebuild to rehash all the information that will basically cause the system either to have very low performance or the system to collapse. So on the right-hand side, you can see here the first chart in which on x-axis, we have different types of faults that we inject into the system, like system hang, that basically we emulated like some part of the system were hanging, actively hanging, perhaps even responding to pings, but not doing any workload. System outages in which things would just crashed. CPU shutdown, in which we shut down, we reduced the computational capabilities of these boxes. Disk saturation, memory saturation, which we saturated all the available disk space and memory. We CPU bar and IO bar simulating threads that were consuming all the resources. And actually, we have 24 different different type of faults that we can inject anytime into the system. Now you can see here we are considering a throughput of 1,000 requests per second. That is what is expected about this scale of systems. So when we inject faults, you can see how much throughput reduction we had. And in blue, you can see in which we had redundancy of 3 controllers per site, and in red with 5 controllers per site. So you'll say, okay, the more controllers that I have, the more resilient I am. Actually, there is a trade-off, because the more control you have, the more information has to be shared and rehashed when you have something going up and down due to failure. This is exactly what's happening here. For instance, if you look the system outage data here, by simply killing one service of one controller, we observed a 32% decrease into the performance of the system. So the system was not able to sustain thousands of requests per second in that case. Same thing if you look down. Even worse, if we increased the workload to 3,000 requests per second, things will even decrease even more sharply. So the same system hang that was causing only 25% decrease into the performance is now causing 58% of performance decrease, and 62% in case you have 5 controllers. So what we trace it back by looking the logs and training our machine learning algorithm. We trace it back to something that in which these controllers were doing. That basically for each small thing that was happening in the network, the entire state synchronization procedure was retriggered. So huge amount of data were flowing, and this Paxos-style consensus algorithm was being executed with huge overhead. So the solution that we identified here is really to quiesce unnecessary state synchronization. If I'm impacting on one single system, I don't need to resynchronize all the possible states, probably. And we leverage the knowledge that we obtained by these chaos experiments to do exactly that, to identify what are the services that you can chaos, and services that actually you need to resynchronize when you have that specific sort of failures. We achieved a 30% increase of the throughput during failover. That basically means for majority of the cases that you see in the upper corner, right corner of this picture, we basically achieved a 0% impact due to failures, which was a good result. Now, same thing if we look at networks. So right now we are injecting system level faults. What happened if we inject network level faults? Like what happened if we inject packet drop or packet reorders, duplication, packet corruption, CRC, retransmission, throttling, latency, and so on? We have another 20 and more different faults that we can inject. And we found out something very interesting, that the 200 millisecond latency for a few seconds on the control plane will cause the unavailability of an entire region. Because then basically these controllers were starting to understand that they were isolated, the so-called split brain problem will happen, and other region will take over, and that region will be cut off. But that, for transient faults, is something that is more damage than good, because then the network will come back again, links start flapping, and then you go back, you go down again, because these are intermittent faults and so on. So what we found here is that basically, first of all, the way that the single threshold, timeout threshold that was used here to fix the system, to detect those faults, was not effective. So you needed something more. You need something which sometimes you really need to pause and buffer the requests that you are getting before you declare that things are failed. Because sometimes it's just a temporary fault. And our data shows that majority of those faults are very transient in time. So if you look now to the data here, you can see really how much is the impact of those faults when you inject a workload of 3,000 requests per second. And you can see that really only when you inject like packet loss and packet reordering and duplication and packet corruption, we basically have no impact on the network. That's expected, right? Because the CRC, the TCP retransmission, and all the other application level protocols are taking care of that. And the network capacity is high, is big. So basically, we can retransmit things and do things to withstand that load. But when you have packet reject or like firewall misconfiguration and packet drops, then you have a problem. And it's really, regardless of how many instances you have your control plane, you cannot really do load balancing of these things, because these things are very difficult to detect. And this is where our contribution was also to understand how we could detect those things like firewall misconfiguration and try to route around that problem without causing any disruption into the injected workload. Finally, I want to conclude with the last slide on what's going on for the continuous testing as a service for enterprise network, like networks for manufacturing. We cannot have robots and agents going around your system and injecting faults, because it's a physical network. So what we do instead, we do have physical robots going around in the network and injecting faults, like creating a bandwidth hogging or creating latency and so on. And this is a hardware that we built that does exactly that. It goes on the factory floor. It basically connects to the network to generate chaos on demand whenever it's needed, just following up what we said in the first slide. So in conclusion, I presented the FICO, which is our tools and our approach, and I would say more of it's a tool and a philosophy applied to production networks for injecting production faults inside production network. And I showed very quickly how this could be used to reduce the time, testing time, and at the same time also to increase the quality of the system. The quality of the system can be increased by many ways. One of these being fault fingerprinting through signal processing using the approach that I presented here today. It was my pleasure, and thank you very much for your time.
Lelio, thank you very much indeed for your insight and fantastic analysis. We've got one or two questions for you if you'd like to stay with us for just a couple of more minutes. And the first question is, I think it refers to the testing you were talking about like 15, 20 minutes ago. The simple question is, how much does this testing take? How long, just roughly?
That's a very good question, and it depends on the system on the test that you want to run. Because there is indeed an overhead for cloning all the things that you need for creating all the testing resources. But if you want to only test a small feature of the network, probably that requires only a few seconds on the telco cloud for running a few additional containers. If you want to test something more complicated, probably you need more computational capacity and time. This tool, the nice thing is that it gives you also information on how much computing resources you need for running these tests. And you run those tests into the idle capacity of the cloud. So saying that I'm only using 20% of the capacity that I have in my telco cloud, 80% is just sitting there doing nothing. I could use that to run many tests in parallel. So the short answer is, it depends. It takes minutes to hours, but that's the scale.
Okay, wonderful. Thank you very much indeed. And let us just see if we've got one more question for you from the audience. Yes, we do. This one's from Rojan. She's asking, how big team of experienced integrators do you need for these tests?
That's another excellent question. That's actually a pain point, because we do need people that are domain experts, at least to start with, because you need to create injectors for that specific system. So you need to know what to inject. And usually those are people like people that are resolving tickets, that are maintaining systems, testing engineers, for instance, of the real production system, software reliability engineers, for instance. They do know what can go wrong. So it's an incremental approach. So you start with a large team that will implement all these injectors, and that, or at least say, okay, this is what we need to inject. And then this team can be reduced because the system becomes very comprehensive. But here, instead of having teams and experienced integrators to integrate this into production system, then you will have people that are many people that are looking to the data that the system is producing to understand how to improve the system. So we remove people from just creating this integration, and we allocate those people to understand how the results that I have allow me to create a better product.
Lovely, perfect. Lelio, thank you so much. A truly international conference today with Lelio Di Martino joining us from Brazil. Thank you for your insight and for your analyses.